Okay, so in this one we're going to take a look at a couple different simple harmonic motion problems. So we talked about simple harmonic oscillators in class, or simple harmonic oscillation. We also use the phrase simple harmonic motion that describes what they do, which we had talked about in class. They have a sinusoidal. In other words, they move like sines and cosines. This is simple harmonic oscillation or motion. We're going to take a look at some of the equations that we had from that. My first one, what we're going to do in this video is take a look at two of them back to back. We're going to find the time it takes for one period, capital T, which equals 2 pi over omega. That's going to be one of our important equations. First one, A, we're going to take a look at a pendulum. So we're going to have a pendulum, a little mass on a rope that can swing back and forth. And in this case, I am totally going to set this pendulum up on the moon. Now, the length of the pendulum, L, is going to be 2 meters. And since I'm on the moon, I need to know my gravitational acceleration. Why do I need to know that? Well, because we're looking at a pendulum, we know that the natural frequency of a pendulum is equal to the square root of g over L. Now the whole thing there is actually under the square root, so be careful of that. It's not square root of g divided by L, it's g divided by L, and then we take the square root of that. In this case, because I'm not going to set this guy up on Earth, I'm going to set it up on the moon. Instead of the more familiar 9.81 meters per second squared, I am instead going to use the gravitational acceleration of the moon, on the surface of the moon, I should say, which is 1.622 meters per second squared. So if I take this, I'm going to say that my total period, the total time it takes for one complete cycle, so that's going to be it. If it starts over here, it's going to go all the way to the other side and come all the way back. Now the total time it takes for one cycle is going to be equal to 2 times pi divided by the square root of g divided by L. In this case, that's going to be 2 pi divided by the square root of 1.622 divided by L, which is 2. I should be putting my units in there, but this is meter per second squared divided by meter, which leaves me 1 over seconds squared. I'm going to take the square root, which gives me 1 over seconds. It's in the denominator, so it'll be flipped up for our period, so we're going to find our answer in seconds. And we find, when we evaluate this, that our total period is right at about 7 seconds. Omega, for the pendulum on the moon, in case you were interested, was equal to about 0.901 inverse seconds. Technically, omega, we could say, is in radians per second, but that's not necessarily that important. Technically, radians are not a unit. But if you deal with rotational mechanics, you're probably very used to omega because we call it an angular velocity. In this case, we're also looking at it as what's called an angular frequency, making it a little bit different than a regular frequency. Alright, so let's take a look at the second one. Spring. I've got a spring, and I'm going to put a mass on it, and it's going to be on a frictionless surface, and I'm going to move it some distance. I believe I'm going to move it 10 centimeters from its equilibrium position. So I'm going to stretch it out by 10 centimeters and I'm going to let it go, and it's going to go back and forth, back and forth. Okay? And I want to know, when I pull it out and let go of it, how long it's going to take until that mass comes back to my hand. Well, it's going to go to the far side and come back. That's one complete cycle. So when I ask the total time it takes for it to come back to my hand, that's just another way of me saying that I want the period. The period is, again, 2 pi divided by omega. In this case, omega for a spring is going to be equal to the square root of k divided by m. And just like before, it's the total quantity here of k divided by m that's under the square root, not just one of them. Okay, well, for this particular one, I'm going to go with K is equal to, what did I go with? 500 newtons per meter. And M equals 0.5 kilograms. So I've got half a kilogram, 500 grams. The 10 centimeters is actually going to be a preview of the next problem that we're going to do, because we're going to bring this guy back up and do a little bit more with him. But for now, I just want to know how long it'll take for the mass to come back to my hand. Well, if I plug these in, I'll have my period equals 2 pi divided by the square root of K over M, which is going to be 500 divided by 0.5. And when I evaluate this, I should come up with 0.199 seconds. In other words, about 0.2 seconds. Now that's happening pretty quickly. And the reason why that is because 500 newtons per meter, that's a pretty stiff spring, it turns out. So it's going to push and pull really hard. And 0.5 kilograms, that's a low mass, so it's probably going to be moved around, pushed around pretty easily. So once you do a few more of these, you can start getting a feel for what is a good value and whether or not it makes sense. This one's a really stiff spring, and it's a really light mass, so it does make sense that it's going to go back and forth really quickly. Oh, and in case you were interested, omega for the spring, if you solve just that, comes up to 31.6 inverse seconds.